So in this session, we will discuss how the charges redistribute in case of parallel plates. Now imagine we are having two parallel plates and these plates are extremely large, which means the area of cross section for these plates would be very huge. Now let's say if we give these two plates charges Q1 and Q2 respectively. So the charges will redistribute in such a way that the electric field inside the plates becomes zero. Now that is because whenever a conductor is given a charge Q, now the entire charge Q goes to the outer surface of the conductor in such a way that the electric field inside the body of the conductor, that becomes zero. Now because of that reason, whenever there are two plates and they are given charges, so they will redistribute in such a way that the electric field at the points which are inside the plate, that will become zero. Now let's try to understand this diagrammatically. So here we are having the first plate. So this is the first plate, plate number 1, and it is having area of cross section of A, and we have another plate which is kept parallel to the first plate and its area is also A. Now the distance between the two plates, now this factor does not define how the charges redistribute. Now let's say Q1 is the charge which is given to the first plate and Q2 is the charge which is given to the second plate. Now after redistribution of charges, now let us say on the different surfaces of the plates, let's say if we assume the charges, so let's say QA is the charge which is there on this surface of the plate 1. So let's say QB is the surface charge on this other surface. On the second plate, let's say QC is the charge over here, and on this outer surface QD is the charge. So this happens after the charge redistributes among themselves. Now QA plus QB, now that has to be equal to the original charge given to this plate, which is Q1. So we can write QA plus QB is equal to Q1. Similarly, the sum of these two charges would be equal to Q2, which is QC plus QD, that is equal to Q2. Now we have to just use the basic funda behind the electrical conductor. So whenever we are having a conductor and we have given charge to it, so the electric field inside the body of the conductor becomes zero. So let's say if we consider this point P as, and this point is point Q. So both of these points are within the body inside the plate. So which means the electric field at both of these points have to be zero. So electric field at point P is equal to electric field at point Q, that is equal to 0. Now all we have to do is find out the expression for electric field at points P and Q, and then we would equate that equal to 0. So now we know that whenever we have a very large plate of having very large cross section and one of its surface has charge Q, so the electric field due to that charge, that is given by sigma by 2 epsilon naught, where sigma is the surface charge density on that surface of the plate. So let's say if Q is the charge on that surface of the plate, so sigma would be written as Q divided by A, and eventually we will get the expression of electric field as Q by 2A epsilon naught, where A is the area of cross section of the given plate. So now in this particular case, there are 4 kinds of charges on the 4 surfaces of the two plates. So let's say we first find out the electric field at this point. Now the electric field due to the charge QA on the point P would be in this particular direction. So let's say if I magnify this expression for better explanation, so let's say if I draw the point P, so the electric field due to the charge QA, let's say if I represent that by E1, so that would be in this particular direction, whereas all other charges QB, QC and QD, the electric field due to all of this would be in the opposite direction. So let's say this is the direction of E2, E3 and E4, where E2, E3, E4 are the electric field at the point P due to QB, QC and QD respectively. So the net electric field at the point P, let's say if I represent by E dash, so that would be E1 minus E2 minus E3 minus E4. So now if I just use the expression for electric field, which is Q by 2A epsilon naught, so E dash can be written as, so E1 would be QA divided by 2A epsilon naught minus QB divided by 2A epsilon naught minus QC divided by 2A epsilon naught, and finally minus QD divided by 2A epsilon naught. So now if I take the terms common, so 1 by 2A epsilon naught would come out as common, so we will get QA minus QB minus QC minus QD. So this entire expression of electric field has to be equal to 0. So now we will put the expression of QB from this expression. So QB would be Q1 minus QA. So this would be Q1 minus QA. And similarly, we can substitute the expression of QD from this formula, which would be Q2 minus QC. So now if I simplify this expression and put the entire expression as 0, so we can find out the value of QA. So on simplification, the value of QA would be given by Q1 plus Q2 divided by 2. So after finding the magnitude of charge QA, we can very easily find out QB as well from this expression. So QB basically is Q1 minus QA. So if I substitute the expression of QA from this expression, so eventually QB can be found out as Q1 minus Q2 divided by 2. So this is the formula for QB. So now we will try to find out how we can find out QC and QD. For that we have to find out the electric field, the net electric field at the point Q, and we would equate that as 0 as we done in this particular case. So now we will find out the expression of electric field at the point Q. So if we see, electric field at point Q would be due to all the 4 charges present on all the 4 surfaces of the 2 plates. So QA and QB and QC would generate an electric field which would be in this direction, and QD would be giving an electric field in the opposite direction. So the net electric field, let's say if it is E double dash is the electric field at the point Q. So that would be given by E1 plus E2 plus E3 minus E4. Now that is because the electric field at the point Q due to QA, QB and QC. So that would be E1 plus E2 plus E3, whereas the electric field due to the charge QD at the point Q would be in this direction. So that would be E4. So this is the net electric field at the point Q. So if we use the basic expression of electric field, so E1 can be written as, so before that if we just take this term 1 by 2A epsilon naught as common, and then we start a bracket, so we will get QA plus QB plus QC minus QD. So this entire expression has to be put equals to 0. Now after that we have to substitute the expression of QB and QD. So QB would be written as Q1 minus QA, whereas QD can be written as Q2 minus QC. Now on simplification of this entire expression, we will eventually get the value of QC as Q2 minus Q1 divided by 2. So this can be written as negative of Q1 minus Q2 divided by 2. Now earlier we had already derived that Q1 minus Q2 divided by 2 is basically QB. So QC can be written as negative of QB. So after we find out the value of QC, QD can also be very easily found out using this expression. So QD can be written as Q2 minus QC, and if we put the expression of QC into this equation, we will get QD as Q1 plus Q2 divided by 2. So this is how the charges redistribute after they are given charges to the 2 plates. So QA and QD, which means the charges on the outer surfaces of the 2 plates. Now those will remain the same, and its value would be Q1 plus Q2 by 2 for both QA as well as QD. Now QB and QC, its magnitude is the same, but they are opposite. As we have seen, QC is equal to minus QB. Now if we consider both of these plates as a capacitor. So the charge on the capacitor is the charge on the inner surface of the positive plate. So in this particular case, QB would be the charge on this capacitor. Now let us consider we are having three parallel plates, each of area of cross section A. Now all of these plates are very large and kept at some distance from each other. So the three plates are given charges Q1, Q2 and Q3. So after redistribution, we have to find out the total charges on all the 6 surfaces of the three plates. So let's try to understand diagrammatically. So this is our first plate and its area of cross section is A, and let's say Q1 is the charge given to this plate, and this is our second plate, plate number 2, and it is also having the same area of cross section A, and Q2 is the charge given to this plate, and this is our third plate, and Q3 is the charge which is given to this plate. So we have to find out how does the charges redistribute among themselves. So the basic approach remains the same. So first we have to assume that at all the surfaces of the plates, we have to assume the charges. So let's say QA is the charge on this surface of the first plate, QB is here, QC, QD and QE, QF. So at the various surfaces of the various plates, we have assumed the charges. So all we have to do is find out the electric field at the point which is inside the plate, and we put that equal to 0. So let's say if we consider this point P, so in the plate 2 it is point Q, so in the plate number Q it is point R. So we have to first find out the net electric field at the points P, Q and R, and we would put that equal to 0, because the general principle is whenever we are having a conductor, so the entire charge goes to the outer surface and the electric field at all the points inside the body of the conductor, that is 0. So that is why at P, Q and R the electric field would be 0. But before that, we can very easily see that QA plus QB, so the sum of these two charges would be equal to Q1. So QA plus QB can be written as Q1. Similarly, QC plus QD can be written as Q2. And for the third plate, we will write the sum QE plus QF. This would be equals to Q3. Now if we try to observe the electric field at point P, now QA would generate an electric field in this direction at the point P, whereas all the other charges QB, C, D, E and F, all of these charges would produce an electric field in the opposite direction, which means in this direction. So now if I try to find out the net electric field at that point P, now the basic expression for electric field would remain the same. So whenever we are having a very large plate of having a very large cross-sectional area, so the electric field due to that charge on one surface of the plate is given by sigma by 2 epsilon naught, where sigma is the surface charge density, and eventually we will get the expression for electric field as Q by 2a epsilon naught. So using this formula, we have to find out the electric field at the point P. So let's say EP, so that would be written as electric field, let's say E1 is the electric field due to QA, and E2 is the sum of all the electric field due to the remaining of the charges. So this can be written as E1 minus E2. So E1 would be basically written as QA divided by 2a epsilon naught, minus E2 can be written as 1 by 2a epsilon naught, and in the bracket we would be having the sum of all other charges, which is QB plus QC plus QD plus QE plus QF. So eventually if I take 1 by 2a epsilon naught common across all the terms, so we will get QA minus QB minus QC minus QD minus QE minus QF. So this entire expression for the electric field at the point P has to be equal to 0. Now we have to substitute the expressions for QB, QD and QF. So QB can be written as Q1 minus QA. Now whereas QD can be written as Q2 minus QC. Eventually we can substitute the expression of QF as Q3 minus QE. So if I simplify the entire expression, we would get the value of QA as Q1 plus Q2 plus Q3 divided by 2. Now similarly, if we consider the point R and if we find out the electric field at the point R due to all the charges and we put that equal to 0, we would get the value of QF. And interestingly, the value of QF is exactly equal to QA, so which is equal to Q1 plus Q2 plus Q3 divided by 2. So from here we can conclude, so whenever there are 3 or any multiple number of plates and we have given different charges to the different plates, so if I add all of those charges and then divide that by 2, so that much charge would be on the outer surface of the outermost plates. So QA and QF, that is given by the same expression. So we already found out the expression for QA. So we can find out QB by this equation. So QB can be written as Q1 minus QA, where QA is Q1 plus Q2 plus Q3 divided by 2. So if I substitute that term over here, so we will get the expression of QB as Q1 minus Q2 minus Q3 divided by 2. So this is the value of the charge on this surface of the plate number 1 after finding out QA. So to find out QC and the other charges, all we have to do is find out the net electric field at the point Q and we put that equal to 0. So now if we consider the charges QA, QB and QC, now all of these charges would generate an electric field at point Q which would be in this particular direction. So let's say E3 is the electric field generated due to QA, QB and QC, whereas all the remaining charges, which is QD, QE and QF, they would be generating an electric field in the opposite direction. So let's say E4 is that electric field. So the sum of the electric fields due to QD, QE and QF, that is equal to E4. So the net electric field at the point Q, so that would be equal to E3 minus E4. So basically we would be using the same expression for the electric field. So if I take the term 1 by 2a epsilon naught as common, so then we will get the expression for electric field at the point Q as QA plus QB plus QC minus QD minus QE minus QF. So this entire expression has to be put equals to 0. Now after that, all we have to do is substitute the expressions of QB, QD and QF. So QB can be written as Q1 minus QA from this expression. QD would be written as Q2 minus QC, whereas QF would be written as Q3 minus QE. So if I simplify this expression after putting equal to 0, we will get the value of QC as Q2 plus Q3 minus Q1 divided by 2. Now if I observe the expression of QC and QB, so we can very easily say that QC can be written as negative of QB. So there is a very important conclusion regarding this statement, which is the pairs of opposite surfaces always carry equal and opposite charges, which means QB, QC, the magnitude would remain the same, but the charges are opposite. Same way QD and QE, the magnitude would remain the same, but the sign of the charges is the opposite. So this was a brief discussion on how charges redistribute whenever charges are given to the parallel plates.